Good morning, chemists. Welcome back. This is lecture 11 of chemistry 132B. I know you guys did a midterm the last time you were active for this course. And, the midterm was perhaps a little bit more difficult than expected for most, even though the questions are really of the same, I would say, order of difficulty, level of difficulty compared to the practice materials you've gotten. But it comes to show that, some of the concepts in quantum mechanics are, foreign to most of us. And so it takes a little while before it sinks in. So, and this is the reason why, in general, the first midterm for this particular course is the fourth time I'm teaching it. And every time the first midterm has been disappointing for people. Okay, so if you feel disappointed about how you did on the exam, then that is very normal. Okay, you were in good company, in fact. And I will go through the exam in more detail maybe later this week. The logistics are such that there's still a couple of people who have to do the midterm, and so I will post the key or the supporting information to the midterm questions on Wednesday. And by that time, I also will release the score. Okay, so you will get all the information you need. And you are encouraged to look over the questions that you did right, the questions that you did not do right. And we can talk about it. So make sure that you take the results of the midterm as an opportunity to learn more about the material, okay? Not as an opportunity to feel disgruntled and demoralized, but really it is a way to identify, okay, so these things I didn't really get. Why not? Let's talk about it. Let's talk about it with the TAs, with me, and make sure that you get it next time around. When the final comes around, some of these questions may come back. So make sure you get those questions by then. Again, don't feel discouraged. This is very normal, okay? The first step is always difficult, but by now you will have a little taste of what this course is all about. And as we go along, you will see some of these concepts will become more familiar to you over time. So keep it up, okay? All right, are there any questions about the midterm, folks, that I can address right now before I continue talking about some new material? Anybody? Will it be curved, is a question. So, I think you know what curving means. Curving means that you take the scores, the numerical scores, okay, the distribution of those scores, and you kind of adjust them based on a curve that was predetermined. And the curve that's predetermined is typically based on the historic performance of people in this class, okay? It does not make a lot of sense to curve every single test or every single assignment because, there's just too much variability and so forth. Curving doesn't add anything to, what you should know or shouldn't know. It is just an artificial means to make sure that the average score of the class is always the same from year to year. That's why, okay? So, but you should take the numerical score as a really good indicator of, how well you manage the material, how well you understand the material. So it is a pretty good reflection of your understanding of the course material. So of course, the higher the score, the better you understand all the stuff. And the lower the score, probably, still some work to do. So take that as a piece of information rather than comparing your performance to everybody else, because at this stage, it's not really too informative. So just focus on your own, understanding. Typically, a grade is a reflection of how well you understand the course material. This is the way it should be, right? So the first order of business is to focus on, okay, let's get better at this. And then in the end, hopefully, that will translate into a good grade. And typically, that's how it works. I've done this now for many, many, many years, believe me. And this is really the best recipe. So don't worry about curving and artificially putting things on a bell curve and so forth, because that really doesn't add anything to your understanding, okay? Understanding first, grade next. All right. All right, if there's no other questions, I'll start talking about some new material, which is, in my opinion, terribly exciting, okay? The first part of this course, indeed, was about quantum mechanics in general, okay? So we haven't really talked about molecules or atoms in particular, but now we're going to do exactly that. So we're going to apply some of the lessons that we've learned, some of the framework that we have been building so far, and apply it to the case of the hydrogen atom first, and later to the case of molecules, okay? So you will see the things that we've learned will come back to us, and they are all needed for us to understand how the atom works, or how we can explain the physical properties of atoms. So one of the things that we talked about right before the midterm was the spherical harmonics. Okay, what is a spherical harmonics? Once again, well, it is the wave function on a spherical surface, right? So we have the wave function that I map onto a spherical surface. We say the potential on the surface is 0 everywhere, so it mimics kind of the particle on the ring situation, but now it's in 2 dimensions because the surface has 2 dimensions. And if we solve that case for the Schrödinger equation, then we found solutions, and those solutions were the spherical harmonic functions. They had a particular shape, okay, and they also had particular energies. The energies only depended on the quantum number L, okay. So those were 2 important lessons that we got last time from this spherical surface quantization. So if you look at an atom, and this is kind of a rendering here, this picture you've been staring at now for a couple of minutes, of the spherical symmetry that the atom has. The atom, of course, has in the middle a nucleus, has a mass mp, and then electrons around it. Okay, so now we're going to start with the hydrogen atom. So that's a pretty simple system because it only consists of a proton. Okay, that's where the plus sign sits, and then an electron that is positioned somewhere in the vicinity of the proton. But the question is, where is it? And that is what we try to address with this quantum mechanical treatment. We're going to try to solve the Schrödinger equation for this system, okay? And that means that we have to solve the problem for 2 particles now, namely the proton and the electron. Previously, we were only concerned about the electron. Now, there's a complication because there's also a proton. What do we do with that? So that's complication number 1. The other complication is that we can no longer assume that there's no potential. There is a potential, and that is the Coulombic potential, because we know there is Coulombic attraction between the proton and the electron. So that is making the whole system a little bit more complicated. And there's another complication, of course, because previously we were focusing on the particle on a sphere where the distance between the origin and the electron is the same in all cases. But now, of course, the electron can certainly move along r. Okay, so r is no longer constant. So that we have a 3-dimensional problem here that we have to solve. And that, of course, is making things rather complicated. So what I'm going to do now is I'm going to show you this very important case. This is actually really important for us chemists to understand. I'm going to show you how to derive the solutions of the Schrödinger equation for this particular system. And the good news is it can be solved exactly, okay? So this is a mathematical treatment that is exact. There's no approximations. Well, maybe a little, but not really much. And we get some real mathematical expressions, okay, defined by this problem. And those expressions, as you will see, explain exactly how the electron behaves around the hydrogen atom. It's really remarkable that this treatment has been so successful, okay? It is really one of the triumphs, in my opinion, of quantum mechanics as applied to the atom. Okay, so don't get lost in the details, okay? I don't expect you to reproduce the derivation I'm going to show you. You don't have to do that. That's not part of this course at all. But I would appreciate, and I think you would too, to recognize where all of this is coming from. Okay, so in the end, we'll just be working with the solutions. We'll not be concerned so much about the derivation itself, unless you are excited about it. I'm happy to talk about the details even more. But we'd like to understand a little bit why these solutions are valid and where they come from. Okay, so just follow along with what I say. If you get a little lost, that's okay. Okay, but just try to do your best to follow the arguments made in order to arrive at the solution of this problem. Okay, so there we go. So first of all, what is the shape of the potential? This is the Coulombic potential. This is an attractive force between the nucleus and the electron. Okay, so the Coulombic potential is written over here, V of R, and you can see it depends on a bunch of constants. Z is the charge of the nucleus. So that's 1 for the proton. Okay, so we just can substitute Z for 1. Every time you see a Z from now on, it's just 1. And then there's the electron charge squared, because both the proton and the electron have the same charge with opposite signs. Okay, so that is the charge squared, and then a bunch of constants, 4 pi, epsilon 0, which is the vacuum permittivity, which is just a number for all intents and purposes, and R. Okay, so it's 1 over R. The thing scales as 1 over R. So the farther away you are, the less attraction there is. The closer you are, the more attraction there is. So this is the Coulombic potential that the particle feels when it's part of the atom. So what do we have to do? Well, we have to solve the Schrödinger equation. And what does it look like? Here is the Schrödinger equation in its most complete form. It's not the equation. I'm sorry. This is just the Hamiltonian. Okay, so this is the Hamiltonian, the operator for energy. What we see here is 3 parts. Okay, and let me just activate my little pen here. Okay, the first part, that is this part right here, is the position of the nucleus. This Rn indicates the position of the nucleus, and we see the kinetic contribution of the nucleus. That's a proton. The proton moves through space, it has a certain energy, and therefore it has a kinetic energy, and that is described by this term. It has the same form as usual. Okay, the same constants, h bar squared over 2m is always there, and then a del squared, which is of course the second order derivative with respect to space. Okay, so here the second term, that's this one over there, that is actually the same term now, but for the electron. Okay, so it's just the position of the electron, of course, that's Re, and then a second order derivative will give us the kinetic energy contribution of the electron. Okay, and then the last term is the potential energy contribution. That's written above. Okay, that's the 1 over R dependence. This R is the relative distance between the electron and the proton. Okay, so that is a relative number. That's not an absolute number. The Rn and Re are absolute coordinates. Now, R is a relative coordinate. It's just a relative distance between Me and MP, the electron and the proton. Again, this I see some comments in the chat box about the distance dependence of this potential energy contribution. It's 1 over R. So the larger R, the less the potential energy is. There's a negative sign here that means attractive. Negative means attractive. Okay, so there's an attractive force between the electron and the proton, but that changes as 1 over R. So the farther you are away, the farther the electron is away from the origin, which is where the nucleus sits, the weaker this attractive force is. The closer you are to the nucleus, the stronger it is. Okay, so this is the Hamiltonian then, and now we have to do a little bit of trickery here, because we have basically 3 coordinates. One is that for the nucleus, 1 for the electron, and then 1 relative distance. So what do we do with this? Well, let's define a couple of quantities that depend on the total of the mass of this system. Okay, so that's the total mass. That's the mass of the nucleus and the mass of the electron, and also the center of mass. So that is kind of like the relative position of the center of this entire unit. Okay, that's given over here. So it's the position of the electron weighted by its mass over the total mass. Okay, and the same for the nucleus. Okay, so the center of mass is not exactly the position of the nucleus. In fact, it's a little off because it depends on where the electron sits. But it's very close to the nucleus because, of course, the mass contribution, so thus the weight of the nuclear coordinate, is much more important than that for the electron, which has a lighter mass, okay, and lower mass. So the center of mass is very close to the position of the proton, but not quite, because there's an electron that's part of the system as well. So we have the total mass and the center of mass, and that's a good descriptor of the total unit, total atom that we're dealing with. But we can also define, of course, the reduced mass. The reduced mass is a definition we have seen before. This is one way in which you can define it. 1 over the reduced mass is 1 over the mass of the nucleus plus 1 over the mass of the electron. Basically, the reduced mass is an effective mass of the system, not the total mass, but the effective mass of the system. And then we can also define the relative distance between the nucleus and the electron, okay? And that's given by R that we already saw. So what we'd like to do now is to kind of maybe take these derivatives that we see here in the Hamiltonian and not rewrite it in terms of the coordinate of the nucleus and the electron, but in terms of the center of mass and the relative distance. If we can do that, then we can maybe focus only on the relative distance and forget about the center of mass. Okay, so let's see if we can do that. And in fact, we can. You don't have to do that. I'm not even going to show you exactly how. But this is the result. So look at the first two terms of the Hamiltonian, the first two, okay? They're written here again, as you can see, right here, the same. Okay, these are the same terms as above. They haven't changed. But you can rewrite these first terms in the following way. Okay, so that's what I've done now. I've written them not in terms of Rn and Re, but in terms of the coordinate R, which is the center of mass, and the coordinate R, which is the relative distance between the electron and the proton. Now, why would I do that? I do that because this term right here, the center of mass, I'm not really so interested in. I don't really care exactly where in space the entire atom sits. What I'm interested in is the relative distance between the electron and the proton. That is what I'm interested in, because I'd like to see the relative position of the electron as it is part of the atom. Not really where in space it sits, but where in space it sits relative to where the proton sits. So I'm all interested in this relative coordinate, and that is what I like to use. Okay, so basically what I'm going to do is I'm going to ignore the first term and only focus on this second term here. Okay, so that means that the Schrödinger equation then will look as follows. What you can see here is the first term, that is that last term in the expression above it. Okay, so that is the kinetic energy operator that now only depends on the relative coordinates, all right, between the proton and the electron. So basically, it is the relative position of the electron relative to the proton. Okay, so effectively, it's the distance of the electron from the proton. That's what I would like to know. That indicates where the electron sits in the atom, not in space, but in the atom. So that's good. That is the kinetic energy of the electron when it's part of the atom. And then the second term stays. It's exactly the same as before. It has not changed. Okay, same as over here. Okay, same as over here. So it is 1 over R. This is the Coulombic potential. So what we see now, there's two terms: kinetic energy operator, okay, and potential energy operator. Putting them in the Schrödinger equation, and of course, that must lead to this eigenvalue equation, where the answer is going to be the energy times the wave function again. So this psi here is what we'd like to determine. Okay, so the psi is what we'd like to determine here. There's a question in the chat about the subscripts. P simply means proton, okay? And N here means nucleus. That means the same thing, okay? I ripped this picture from somewhere else. So there's like a discrepancy between P and N, but they really mean the same thing here. The nucleus is the proton, okay? The nucleus is the proton. That's the same thing. Okay, so the Schrödinger equation here below is what we would like to solve, okay? This is what we'd like to solve. Question in the chat box: why does the center of mass not matter? That is because we're not interested in the kinetic energy contribution of the particle as a whole, okay? This particle can move through space, can flow through space with a certain kinetic energy. I'm only interested in the kinetic energy and the potential energy that the electron feels inside the atom, okay? Not inside the entirety of space, but just when it's part of the atom alone. So if I isolate the atom and keep it still, okay, then there's no change of the center of mass at all, and so the whole first term is not contributing at all, okay, because there's no change. That means the delta square of R, capital R, is going to be 0. So effectively, if I keep the entire atom motionless in space, I'm only concerned with the relative coordinate, and that's why this first term can be set to 0. All right, so let's focus on the Schrödinger equation. Here it is once again. Same equation, no change, okay? That's what we like to solve. first order of business is this. I'm going to look at this del squared, and I'm going to write that thing out, okay? And we have seen this thing before. Maybe you have forgotten about it. That's okay. But let's just write it out again. This is what it looks like. In addition, okay, so we do two steps here from the first equation to the second equation. The first is writing out this del squared thing, okay, which has now dependence on the second order derivative respect to r, and this lambda squared, which has the dependence of the angles theta and phi. Hopefully you remember that, okay? The second part that I'm doing, I'm going to multiply this entire equation by the inverse of h bar squared over 2 times the reduced mass. The mu is the reduced mass. Okay, so when I do that, I get this term here all the way on the right. Okay, that's exactly the same as last time. Last time, hopefully you remember that, when we solved the problem for the particle on the sphere, we simply said that this term is going to be 0 because r doesn't change. Okay, constant r means this whole thing is 0. And we also said the potential is 0, so it means this term was 0. Okay, we only left with this derivative term, and then on the other side we had the energies with the prefactor. This was the problem of the spherical harmonics, okay, particle on a spherical surface. That was the exact Schrodinger equation, but now we have two extra terms, okay, that we cannot ignore, namely the change as a function of position and the Coulombic potential contribution that you can see here. Okay, so how do we solve this problem? How do we solve this problem? Well, what I'm going to do is I'm going to take this equation, which looks pretty horrendous, but hopefully this explanation will tell you what these independent terms mean. They have meaning, of course. And I'm going to solve this thing by assuming a certain shape. Okay, the shape of the wave function that I'm assuming is the following. First of all, the wave function that I'm trying to solve has 3 coordinates: the distance between the nucleus and the electron, theta, and oops, that's wrong. That should be phi, not psi. Okay, let's correct that. That looks terrible. That should be a phi. Okay, not psi. Okay, so it has, of course, 3 coordinates. These are the spherical coordinates of the electron in the atom. I'm going to say the following. There is a function that depends only on r, that's capital R, this guy. And then there is a part that only depends on theta and phi, and that is the same as the spherical harmonics. These are the spherical harmonic functions. Why do I say that? Because I recognize this part here is really the spherical harmonic contribution, okay? So I want to keep it in there. I recognize the symmetry of my atom. It has spherical symmetry, so I want to keep it in there, and I'm forcing a solution that has that in it. This is a guess, but it turns out to be an excellent guess. In addition, of course, there is a part that must depend on r, and that's, of course, because there's a dependence here on r in the first term, and also a dependence on r in the second term. Okay, so there must be an r dependence, and that's taken care of by this capital R of r. I'm going to put this thing in there and see what happens. Okay, so here we go. I'm substituting psi above here. I'm going to put in this shape, r times y. That's given over here. Okay, I'm just substituting psi for r times y. Okay, nothing terribly exciting going on here. But now I'm going to do the same thing here in the second term, and now something interesting happens. Why? Because, as you can hopefully see, if I do lambda squared, that was the spherical harmonics operator, if you want, the Legendrian. If I'm operating that on r times y, this Legendrian only depends on theta and phi. So when it operates on r, it doesn't do anything because r has no theta and phi. And that means it only operates on the second part, okay? On the spherical harmonic part, okay? There. And that means that I have a solution. I don't know if you remember this from last time, but there's a solution when this thing operates on the spherical harmonics, okay? That was h bar times L plus 1. Hopefully you remember that, okay? And then times the function r, y. Because the spherical harmonics are eigenfunctions of this Legendre operator. That was the whole point from the spherical harmonics discussion that we had last time. Okay? This is good, actually, because that means now I can evaluate the second term quite nicely. And here it is. Okay, here it is. It's L times L plus 1 over R squared. Oh, I made a mistake. I apologize. It should not be an H bar there. This H bar should not be there. Apologies. Okay, so that's the second term. The second term, this term here, I use this trick up here, and that's where the L times L plus 1 comes from. Okay, because again, this lambda square is the Legendre operator. When it operates on y, y is an eigenfunction with the eigenvalues L times L plus 1. This R square comes, of course, from the prefactor that was already there. Okay, that's it. All right, so that's good. The second term I kind of did something with. What about the third term? I cannot play any tricks here, so that's just the same as before, where psi is R times y. Okay, and then, of course, I have my energy, where psi, again, is R times y. All right, so how is this going to help me? Well, it's going to help me a little bit, because check this out. Look at this. I have here an equation that has a y here, a y there, and a y there, and a y there, okay? And in all of these prefactors, there is no dependence on theta or phi, which is what y depends on. So I can simply divide out. I can divide out the y. That means the whole theta and phi dependence is kind of like factored out, okay? And I only retrieve something that depends on r alone, okay? So here's the reduced equation where I divided out y, okay? And then I collected the terms. These two terms are now collected between parentheses, okay? So this is the Coulombic term here, there's the Coulombic term, and this is the term that I'm getting from this term, the second term here above. Why do I collect it like this? Well, this term here is actually very important. This is now my effective potential energy term. It has two contributions here, okay? Two contributions. The first one is, again, the Coulombic contribution, the attractive force between the electron and the proton. The second term is dependent on L. What is L? Well, L is a measure of the energy, the angular energy, the energy of the particle on the sphere. In fact, L is the quantum number for angular momentum. So the larger L, the more angular momentum. So when L is going to be bigger, that means that this term is going to be bigger. The more angular momentum, the more this term contributes. Now look at the sign of these two contributions. The potential energy term, which we know is attractive, has a different sign than the second term, which depends on angular momentum. Okay, so the first term is attractive, the second term, therefore, is repulsive. That means that the higher the angular momentum, the more repulsion the electron experiences. So there's an attractive force due to the Coulombic interaction, and there's a repulsive force due to the fact that the particle has angular momentum. How can we understand this? Well, this is what we call, the second term is what we call the centrifugal force, okay? Because the particle spins around with a certain angular momentum, and you probably know, the higher the angular momentum, the more it wants to go away from the origin, right? That's just like if you have a ball on a piece of rope and you swing it around, you know the ball wants to go away, okay, wants to fly away. That is the repulsive force that it experiences of the centrifugal force. So this is the centrifugal force, which is having the opposite sign compared to the Coulombic force. These are the two forces that kind of are fighting it out with one another for the attention of the particle when it's part of the atom, okay? So we have now two terms. The first one is in this box. That is the total potential energy contribution that a particle feels. There's two parts to it, like I just said, attractive and repulsive. And then there is the kinetic term, the kinetic energy term of the electron because of its position r. Okay, so again, kinetic energy and potential energy contributions here. All right, so we have to solve this problem here, and that is not necessarily very easy. By the way, I can define this thing in the red box as follows. I define that as an effective potential energy, as indicated over here. Okay, so that is one way of combing these two things together and then writing it as a potential energy contribution to the Schrödinger equation. So let's clean this up and write it as follows. This is what I'm getting. I'm going to write a new function, capital Pi, and that is the solution that I want, that is R, okay? R is what I want, remember, the total wave function is this, right? Just to be sure that everybody understands, this is my total wave function. But I already have the second one. That's a spherical harmonics. That part is already solved. Those are the solutions from last time. The only thing I'd like to know is R, okay? And so this is what I'm trying to solve. Now, to solve the actual differential equation, it helps to define a kind of a help function that is defined as little r times this solution that I'm after. And if you do that, then the differential equation looks like the one below. It's a pretty clean differential equation. Hopefully you agree with that, okay? So although this guy here has actually an r dependence in it, so don't be mistaken or misled that this is a very simple equation. It's actually pretty complicated. But in any case, in this form, it looks somewhat manageable, and turns out that we can find solutions to the resulting differential equation. What are solutions for this? Well, we can solve for pi and then simply multiply by r, and then we find the solutions for r. And the result is given over here. This is the result for the radial part of the wave function of an electron when it's part of the hydrogen atom. Okay, so let me just walk you through this, because this looks at first sight, of course, like a terrible mess. But all these things have meaning. So let's decompose that. So hopefully it'll look a little less scary to you next time you look at it. The first term right here is simply some sort of a prefactor that depends on a bunch of numbers. All of these numbers are given based on a problem. All right, so you know the number n, which is the principal quantum number, and I'll say a few words about that. L is the angular momentum. So these are two quantum numbers, n and L, that you must know, of course. You must know what you're talking about. What are the quantum numbers? Once they're given, you can plug them in and calculate what the prefactor is, okay? Because it only depends on n and L. Z, again, is 1, and everything else is just a number. A here will be defined right below in 2 seconds. Okay, so that's the first term, bunch of constants. So don't be afraid of it. The second term is rho times L. What is rho? Rho is something that is directly proportional to R. So it's just R with some kind of prefactor. And I will define it below here in 2 seconds. Okay, so this is just basically R to the power L. And L is the quantum number. Okay, so that's it. Then this function here, which is called the associated Legendre function, difficult word, but it is simply a function that comes from the table. Okay, so I'll show you what these things look like, or I show you the effective result of what R looks like if you fill out the numbers from Legendre, sorry, not Legendre, Laguerre tables. And then finally, I see this one here. This is the last term. It's a decaying exponential, where I see the rho again. Rho is proportional to R. So the larger R gets, the smaller this term becomes. All right, so what we see then, prefactor 1, then a function that goes up quite rapidly. When L is larger than 0, this function increases quite rapidly away from the nucleus because it goes up, right? It's an exponential. So it goes up quite rapidly. And then I see a term that is kind of a polynomial. This is like a zigzaggy function, basically an oscillating function. This will give rise to nodes, as you will see. And then finally, there is the decaying exponential, which makes sure that at infinity, where rho is going to be infinite, this whole thing is going to go down to 0. Okay, so that of course must make sense, because this wave function here, the radial wave function, must go to 0 if you go far away from the nucleus. That's what it says. Okay, now let's define the unknowns here, because this is a little aggravating that we don't know what they are. Here it is, rho prefactor, once again, times R. Okay, so really rho is just what R is, times some kind of constant in front of it. All right, so you can compute, typically you have those values available, and you just fill them out, and you know what the distance, the relation between R and rho. And then this A is literally just a constant, which is defined by numbers that you know. Of course, we know the reduced mass of the hydrogen atom. That's easy because we know the masses of the electron and the proton. The vacuum permittivity is known, H bar is known, and so forth. Okay, so this is all known. A is just a number. We plug it in and can compute it. Now, what do we get if we just fill out some of the numbers? Remember, N and L are quantum numbers. N is the principal quantum number that we all know about, but it rolls out of this equation. Here's where the N comes from. Maybe you've wondered sometimes, why do we have an N? What is that? Well, the N comes from this. From solving the Schrodinger equation, we get solutions, and they have indices, and one of these indices is N. We have given it a name, principal quantum number, but it follows from this mathematical reality. And then the L, of course, is the angular momentum quantum number that we already know. Okay? The E, indeed, is the electron charge. E is the electron charge. Okay? Every time you see something like this, E squared or E in a formula that's a constant, then E is always the electron charge. Okay, so let's look at the shape of these R, N, L. Okay, so remember, it's a function of rho, but rho is really R times a constant. So principal quantum number, the lowest possible one is 1, not 0, but 1. Okay, so that's important. That's the lowest one. And then the lowest L is going to be 0. That's the 1s orbital that we all know of. This is the radial part of that wave function. It is a constant. This constant follows from this complicated formula up here, but it really reduces to a very simple, bunch of constants here. This is not so, difficult looking. Then 2 times this decaying exponential. So the 1s orbital is just a constant, okay, and then it decays away from the nucleus. So the electron wave function simply is a decaying exponential. The farther away from the nucleus, the less amplitude this wave function has. Then when n is 1 level up, 2, then L can have 2 values, of course, 0 and 1. Those are the 2s and the 2p radial wave functions in this case. And the radial wave functions look the same. They have, again, a decaying exponential, a kind of a prefactor, which looks a little bit different now, but not by too much. And then a factor that depends on 2 minus rho for 0, for 2 and 0. So there's actually an extra node. A node means that if I make rho 2, this is going to be 0. So for a certain position of R, this thing goes to 0. And that means that I have a value of Rn, L that is going to be 0 on the x-axis, so to speak. And that leads to a node. We'll show you an example on the next slide what that means. And then the other solution, 2, 1, has a rho dependence in it. So it goes up according to rho, it goes down according to this decaying exponent. Okay, so these functions have just shapes, and we'll show you what they look like on the next page, and they follow directly from this solution of the Schrodinger equation. Now let's have actually a physical picture of what these things look like. Here we go. All right, they look familiar, hopefully, but the new thing is that hopefully understand where these things come from. They are true solutions of a mathematical problem that is defined according to our physical problem, namely solving the problem of the electron around the proton. So the 1s is R1, 0. Remember, this is only the radial part. This is only the radial part because a total wave function is R times the spherical harmonics. Okay, so I'm not focusing on the spherical harmonic part. This is only the radial part. This is how the wave function changes as a function of the radial coordinate R. All right, and what we see here for 1s, which is n equals 1, L equals 0, that is a decaying exponential. It starts at a certain value, and then it decays away from the nucleus as you go farther out. Okay, so far away from a nucleus, the amplitude is going to go to 0, as expected. Now, if you go to R2, 0, where n is 2 and L is still 0, okay, remember, if L equals 0, that means you are dealing with an s orbital. Here again, L equals 0, that means an s orbital. So it's still s, but now it's now 2s instead of 1s. The difference between a 1s and a 2s is, maybe you remember that from the previous slide, that there is now a term, this comes from 2 minus rho term in there. That means that there's going to be a position along the r-axis where there's going to be a 0. That's this 0 right here. Okay? We call that a node. There is a node here. So it goes from a positive number, swings through the axis, goes to negative values, and then comes up again on the other end. Okay? So The difference, the main difference between a 1s and a 2s is that the 2s makes a swing. Okay, just like we have seen before for the particle in the box, a harmonic oscillator, it makes more swings if the principal quantum number goes up. And it's the same here, L equals 0 once again. So it's still an s orbital, the 3s. I've now 3 here, and you see an extra swing. So there's 2 nodes, one there and one there. Okay, so this is analogous to all the quantum mechanical problems that we have solved thus far, where the higher the principal quantum number, the more swings the function is going to make. All right, and then it decays, of course, to 0 if you move farther out. So that's one thing. Now remember, the wave functions I talked about so far only have L equals 0. What does it mean? That means the following. Remember this term, this extra term, centrifugal force. Centrifugal force depends on L plus 1, okay, 1 over R. That's the term, all right? 1 over R squared, sorry. And so when L is equal to 0, this whole term here, this whole term is going to be 0. That means there is no centrifugal force. There's only an attractive Coulombic force. And that means that it's very favorable for the electron to be close to the nucleus, because that's where the attraction is the highest. And that's what you see for all s orbitals. But if I'm now increasing my L value, so this is the first wave function I'm considering with L is not equal to 0. So this is not a p orbital. Sorry, not an s orbital, but a p orbital. Okay, because all p orbitals have L equals 1. That means that there's now a centrifugal force. That means it will swing away the particle from the center, from where the proton sits. Okay, so that's the reason why here at position 0 you have a node. It won't go there because it's basically it spins away from the origin. That's a centrifugal force component. Okay, so you see it starts at 0, and then it goes up again, and then it comes down farther away from the nucleus. So there's a key difference between the s and the p orbital, and that's due to the fact that the particle has angular momentum. That's this term right here. If it has angular momentum, it can be close to the nucleus because it basically swings away. There's a repulsive force, an effective repulsive term due to the fact that it has angular momentum. The same is true for the 3p. Okay, the 3p and the 2p look very similar. The main difference is that there is now a node, an extra node away from 0. All right, so that is of course understandable because the quantum number goes up. The principal quantum numbers go up. That means more nodes on the radial coordinates. And here's the first d orbital, the 3d. It is a 3,2, so n equals 3, L equals 2. That is a d orbital, and it looks like so. It also has angular momentum, and that means that it has a node at 0. Okay, so this is the first d orbital that we encounter. There's also a 4d and a 5d, and of course they have extra swings, extra nodes along the radial coordinate, as we see for the other wave functions. So these are the general trends along the radial coordinate. All right, so these are the wave functions then, the radial wave functions, times the spherical harmonics, which we already know what they look like. And so we have a complete solution now for psi. This is the wave function of the electron when it's part of the hydrogen atom. One more thing before we close is knowing the wave function is one thing, but I also would like to know what their energies are. Remember, the Stirling equation gives me 2 things. One, the wave functions, but also the E's, the energies. So what are the energies? Here's my wave function. I'm writing it out fully now. All the quantum numbers, the principal quantum numbers, L, that is the angular momentum quantum number, and then ML, also called the magnetic quantum number, depending on angular momentum, and that's called ML. Okay, we see that there's a radial part, which depends on 2, only on N and L, and then the spherical harmonic part, which depends on L and ML. So the spherical harmonic part does not depend on N, but it does depend on ML. Okay, so here's again the values. N starts at 1, then goes to infinity. Okay, L is starting at 0 and then runs all the way up to N minus 1. So when N equals 1, there's only one value, namely L equals 0, right? And then ML has the same relation as before because it hasn't changed. It's slaved to whatever L is, right? And so it runs from, minus L to plus L, or from 0 to plus minus L. That's the same. Okay, so there's a total of n values of L. So for each n, there are n L values. Okay, so when n equals 2, there's basically 2 L values. And when n equals 3, there's 3 L values. And for each L, there is 2 L plus 1 values of ML. I think you have seen these relations before. Okay, so now what are the energies? Here are the energies. And this is a kind of a really remarkable conclusion. First of all, maybe it looks scary at first sight, but this is, again, just a bunch of constants. Okay, Z is 1, mu is a reduced mass, E is the electron charge, 32 is a number, pi is a number, electric permittivity, vacuum permittivity is also a number that you can look up in a table, and h bar is a number. So basically just a constant, and then 1 over n squared. Why is this remarkable? It's remarkable because I have 3 quantum numbers that define my wave function, the shape of my wave function. It's a 3-dimensional wave. It depends on these quantum numbers. It's a 3-dimensional wave that shows quantization in space. Okay, there's regions in space where the values are high. There's regions in space where the values are low. Okay, so it has wave-like properties with nodes and everything, depending on whatever n, l, and ml are. However, the energy of these waves only depends on n. It does not depend on l and ml, and that is really elegant in a way. Okay, you wouldn't expect that just by looking at the problem, but because of the high symmetry of the atom, which, because it's a beautiful spherical system, we only have one quantum number that defines the energy here. All right, and so what are these levels? And these are the levels that you are familiar with. Okay, for n equals 1, the lowest possible wave function, of course, which has L equals 0 and ML equals 0. That's the 0-point energy that the electron can have. And that is what you get if you fill out 1 for this value n. That is the energy that you get. And then if n equals 2, then there's 2 values for L, of course, 0 and 1. And that means that if L is 1, there's 3 values of ML. That means you have a total of 4 states that have the same energy, because these energies only depend on n and not on L and ML. So I have 4 states that are degenerate. All right, and if n equals 3, again, there's now 3 values of L, namely 0, 1, and 2. Okay, and then when L equals 1, there's 3 ML values. When L is 2, there's a total of 5 ML values. And that means that there's a total of 9 states that have the exact same energy. They are degenerate, 9-fold degenerate, because they only depend on whatever n is and not on what L and ML are. So there's a so-called degeneracy factor, G, okay, that basically says how many states you have of the same energy. And so for each value n, if I count up from L equals 0 to n minus 1, that's what I do here basically. That's exactly the same here. This is just basically counting up how many states you have. 2L plus 1, run over all possible values of n, sorry, all possible values of L. That gives me n squared. All right, so that's an easy formula. So whatever n is, you have n squared levels that have the same energy. So for n equals 1, it's 1, n equals 2, it's 4, n equals 3, 3 squared is 9. All right, so that's a beautiful result. Okay, so the hydrogen atom, because of its high symmetry and no other factors that mess this up, we'll see there will be some factors that mess this up for polyelectronic atoms. But for the hydrogen atom, you have this beautiful symmetry that gives us a wave function that depends on 3 quantum numbers, but the energy depends only on 1. Okay, so we have a high degree of degeneracy. Okay, that's it for now. We'll continue, of course, our quest and understanding of what it all means, and we'll move along to explain properties of the hydrogen atom and properties of atoms that have more than 1 electron later on this week. Okay, so thank you, folks. Thanks for staying with me with this course. I know some of you may be unhappy about the result of the midterm, but you know, like I said, it's part and parcel, and it's going kind of exactly as I expected it to go. So no worries at this point. Thank you.